Welcome to lecture 9 of module 4. In this module, we have been discussing about the convective heat transfer, different types of convective heat transfer correlations. Then we have discussed about analogies, and then we are concentrating on boundary layers. And in the last lecture, we have discussed that how to develop the equations for boundary layers. We have developed equations for hydrodynamic boundary layers, and we found out how to find out from the equations developed, how to find out the exact solution in case of hydrodynamic boundary layer. The solutions in the form of wall shear stress, in the form of say friction coefficient, or in the form of boundary layer thickness, that we have already seen, and which is being proposed by Blasius how to solve this. Now, what we are left out with this is that in case of exact solutions, what is happening for energy equation. If we try to see that, today we will see that how the energy equation will be derived in case of boundary layer, and then how to get a solution to get the expression for heat transfer coefficient or Nusselt number. And one thing I should tell you again, that these analyses or that these models what are being developed, these are all applicable to laminar boundary layer only. In case of turbulent boundary layer, there is a problem of eddies to come into picture, and therefore, in case of turbulent boundary layer, the equations for heat transfer is usually taken by from correlations. Already we have discussed a problem related to that, where we have shown that in case of turbulent boundary layer, what kind of equation should be used, in case of laminar boundary layer, what kind of equation should be used, and then we have seen that when a flow is over a flat plate, how to get the final or average heat transfer coefficient and get the average total value of the heat transfer rate. Now, we will concentrate in this lecture. First, we will concentrate on energy equation of the thermal boundary layer. Already we have discussed what is the thermal boundary layer in the last lecture. So, if we just consider again a differential element in the thermal boundary layer, and I will just write that differential section here and say this is your the delta y or dy, you can say, and this is your say dx. So, we can say that this is your x direction, this is y direction, and we have that in this we can say that energy in this case, energy input is rho V x is the x direction velocity, C p into t, okay, and then this is the convective in, plus you can have that this is the diffusive in, okay, the q x, fine, and that is coming at point x. And similarly, energy out will be rho V x C p t plus q x at say x plus dx, and here from the bottom it is going coming like rho V y C p into t plus q y at point y, and this is coming as rho V y C p into t plus q y at point y plus dy. So, we can understand that this is the energy is coming in the form of convective input and diffusive input, going out convective input output, diffusive output. This is the convective input, diffusive input, convective output, diffusive output at point y plus dy. Okay. And then net heat generation by diffusion, by viscous dissipation is nearly equal to mu into del V x by del y, sorry, I will write in the other line, is equal to mu into del V x by del y whole square dx by dy, and we will assume to be 0. So, that means the viscous effect is negative, that is viscous dissipation is neglected. Okay. Now, once we do that, and we also know that q x can be written as minus k into del t by del x, and q y can be written as minus k into del t by del y. These are based on the Fourier's law, and these q x are, these are the fluxes per unit area. So, now if we just go the steady state energy balance in this control volume, what we get is, just putting all these equations together, we can get like this, that del x of V x into t plus del y into V y into t is equal to alpha into del square t by del x square plus del square t by del y square, where alpha is k by rho C p, which is nothing but thermal diffusivity. Okay. So, this is what is happening. Now, what we will try to understand is, now if we further go ahead with this equation, then we will have that t into del V x by del x plus V x into del t by del x plus t into del V y by del y plus V y into del t by del y, okay, is equal to alpha into del square t by del x square plus del square t by del y square. So, now we have to do some application. So, you can write that, or t into, if we write del V x by del x plus del V y by del y, okay, sorry, then plus V x into del t by del x plus V y into del t by del y is equal to alpha into del square t by del x square plus del square t by del y square. Okay. Now, this part is 0 from continuity equation. So, we are using the continuity equation also, even when we are going for energy balance equation, we are using the continuity equation. Then we can get that V x into del t by del x plus V y into del t by del y is equal to, now what we will do is that del square t by del x square is much less than del square t by del y square. That means, the assumption is the variation in the temperature, the second derivative longitudinal gradient is much smaller than in the transverse gradient based on that. So, what we can write, that then we will neglect, this one is neglected because of that reason with this assumption. So, then we will write that it is alpha into del square t by del y square. And if you see in case of, so this is becoming the energy equation, and if you see exactly the similar kind of equation that we have developed for momentum. So, what is the momentum equation? It is, that is V x into del V x by del x plus V y into del V x by x directional momentum, del y was equal to mu to del square V x by del y square. So, this is your energy equation that we got, and this is your momentum equation that we have discussed, we have found out in the last class. We have done the derivations. Now, in case of energy equation, we have the boundary conditions. Boundary conditions at y equals to 0, we will take T is equal to T w, that is the wall temperature, okay, and y is tends to infinity, then T is equal to T infinity, and x equals to 0 also, T is equal to T infinity. X is equal to 0 means that is the leading edge, at this point x is equal to 0 and the fluid is flowing like this. So, there is no, everywhere the temperature is T infinity, free stream temperature of the fluid, and here is the boundary layer that is being formed. So, y tends to infinity means, so somewhere in this this boundary layer thickness, as we move on boundary layer thickness. So, it is beyond the boundary layer thickness. This is the idea of that, t is equal to t infinity. So, this is the conditions of the boundary conditions. Now, based on that, now what is done, it is this energy equation is also non-dimensionalized with the variables. It is as we have done in case of momentum equation. So, eta is equal to y by nu x by v infinity. Now, what I will write, many times I am writing either. So, it is basically v x v infinity or v x infinity are same. So, previously we have written something on v x infinity. So, we now onwards we will write as v infinity instead of writing as v x infinity. So, it is the v infinity is nothing but the free stream velocity along x direction. Okay. So, this whole to the power half, that is eta, and T bar dimensionless temperature is equal to T minus T w, that is the reduced temperature, and dimensionless temperature also this. Now, what from there we can write that del T by del x is equal to del T by del eta into del eta by del x, and that is equal to del T by del eta into y into v x. I will now write infinity only v infinity by nu x y into v infinity by nu whole to the power half into minus of half x to the power minus 3 by 2. So, this can be exercised, this can be done. These are not simple things, only just getting the derivations. It will be del T by del y into del eta into del eta by del y, and that is equal to del T by del eta into v infinity by nu x whole to the power half, and then we can get del square T by del y square is equal to del square T by del eta square into v infinity by nu x. That is what is the. So, finally, after substitution, so we get d 2 t bar d 2 t by d eta square plus half into Prandtl into f, that already we have defined in the last lecture, dt by d eta equals to 0. Now, in terms of dimensionless temperature, or rather already we know in terms of T bar, it is becoming d 2 T bar by d eta square plus half of Prandtl into f dt bar by d eta, this is equal to 0. So, this is becoming the dimensionless equation of the energy equation is converted into dimensionless equation form, where we know that T bar is equal to T minus T w by T infinity minus T w, and then our boundary conditions changed. So, we can say that eta is equal to 0, T bar equals to 0, and eta tends to infinity, T bar is equal to 1, or rather tends to 1. So, like that way, if we see that, then the solution of the above equation is T bar is equal to T minus T w by T infinity minus T w equals to 0 to eta f double dashed to the Prandtl into d eta by 0 to infinity f double dash to the power Prandtl into d eta. Okay. And interestingly, when Prandtl is equal to 1, then T bar is equal to, we can say V x, it will become integral 0 to eta f double dashed d eta by 0 to infinity f double dash d eta, and that is equal to f dash, derivative of f double dash is f dash 0 to eta by f dash 0 to infinity, and this is equal to f dash eta, and which is equal to V x by V infinity. So, we can say that dimensionless temperature and dimensionless velocity, they are having the they are same, they are coinciding with each other. That is what we have already seen, that for Prandtl number 1, the both thermal boundary layer and hydrodynamic boundary layer should coincide over each other, and that also we can see from here. So, this we can say that is equal to say V x bar dimensionless velocity. Okay. Now, they are coinciding with each other. Now, further we know that minus k into del t by del y, that is at y equal to 0, is nothing but the heat flux from the wall of the surface in case of boundary layer flow. From the wall of the flat plate, the heat flux is taking place in case of heating a fluid, okay? And that is equal to, we can say that q w wall, which is a function of x only, because t is a function of x. So, this q w would be a function of x, and this we can write as h x into, we know that Newton's law of cooling, T w minus T infinity, whereas h x is the local heat transfer coefficient, that we know. So, from there we can say that h x is minus k into del t by del y, okay, at y equals to 0 by T w minus T infinity. So, that is why it is also sometimes called that. So, Nusselt number, if we can say from there, we can say that nu x is equal to h x x by k, okay, and that we will write as minus the k cancels. So, what we will get is del t by del y at y equal to 0 divided by T w minus T infinity by x. Okay. So, this says, we can say that it is temperature gradient at the wall divided by temperature gradient at the bulk. So, this is the another definition of Nusselt number. Now, here nu x is called the Nusselt number, this is a local Nusselt number nu x. So, we can find out that nu x is equal to h x x by k, and that is happening to us as this can be written like this. So, again rewritten x into now this by this is the t bar. So, del t bar by del eta, or rather y at y equals to 0. So, this can be written as x into del t bar by del eta at eta equal to 0 into del eta by del y. So, from there we can side, if we put these expressions, then we will get that nu x is equal to this to the power Prandtl number at eta equals to 0 by 0 to infinity f double dash whole to the power Prandtl d eta into R e x whole to the power half. Now, the numerical value of is been computed, and it has been found out that nu x is equal to 0.332 R e x to the power half and Prandtl to the power 1/3. So, just by computing the values of this part, it has been found that Nusselt number can be found out as 0.332 into Reynolds to the power half and Prandtl to the power 1/3. Okay. And this is after just computing the values of this integral and all these things, this can be obtained. And we can understand that this part has already been discussed long back when we have, particularly in lecture 5 of module 4, where we have discussed that this is the correlations from exact solution. This is coming from exact solution of the energy equation. Okay. Now, if we try to see that average Nusselt number, then it is becoming then H average L by K. So, average Nusselt number based on average heat transfer coefficient for the overall plate, and this becomes 0.664 REL based on Reynolds number based on the length into Prandtl to the power 1/3. So, this part already we have discussed. However, we have seen that how we can get the expression for Nusselt number, and from there by doing the computation of this part we can find out this expression as the expression for Nusselt number in case of exact solution of exact analysis or solution of the energy equation, exact solution of the energy equation. Okay. And then we can see that actually the equation is exact when Prandtl equals to 1, but for 0.5 less than equal to Prandtl less than equal to 50, the calculation of Hx, okay, local heat transfer coefficient, is within 2% of error. So, this is a very good prediction of the values, that is why it is called exact analysis of the things. And then we also already have told you that delta T is the thermal boundary layer thickness, and delta is the hydrodynamic boundary layer thickness, and then we said that delta by delta T is equal to Prandtl to the power 1/3, and we know when Prandtl is equal to 1, delta is equal to delta T, and thermal and hydrodynamic boundary layers coincide when nu is equal to alpha, momentum diffusivity is equal to thermal diffusivity. Then Prandtl less than 1 means nu less than alpha, and then delta less than delta T. So, if the momentum diffusivity is less, then momentum thickness is also hydrodynamic thickness is of displacement, momentum thickness is also, momentum boundary layer thickness is less, and this is and if Prandtl greater than 1, then nu is greater than alpha and delta is greater than delta T. Okay. So, this is, and also we have seen, we have to discuss that for Prandtl to be much less than 1, this is happening for liquid metals, okay, and for Prandtl much greater than 1, it happens for polymeric fluids. This already we have discussed, but it is for again for keeping a or giving a reminder to these particular things. Now, this is what we have discussed. These are called exact solution, but there is another solution that is called a simpler solution to this particular case, and which is called that integral method of analysis. So, we will concentrate on that part, integral method of analysis. So, this becomes a very important thing from the analysis point of view of heat transfer calculation of heat transfer coefficients, particularly when a fluid is flowing over a flat plate, and not only heat transfer coefficient, also for calculating the shear stress and all other things for only for hydrodynamic flow. Now, what happens in that case? As I discussed already, I told in the previous case that in the integral method of analysis, or it is also called as approximate method of analysis. This is called approximate analysis. This is called approximate because here a velocity distribution is assumed. And in this integral method, that means we are considering the balances, momentum or energy balances for a total boundary layer, integrating from the x is say y equal to 0 to y is equal to the boundary layer thickness. So, we do the integration and find out what is happening to the energy equations as well as momentum equations. So, to do that, let us first concentrate on a combined approach. If I try to see this, say it is like this, this is the plate, okay, and there is so boundary layers. I have drawn two boundary layers. This I will say that hydrodynamic, and this I am saying as thermal. So, thermal boundary layer is lower than the hydrodynamic boundary layer, and say above this is say total height is h, where and this is at any point, say this is delta, and at any point this is delta t, and h is greater than delta, and which is greater than delta t, thermal boundary layer thickness, and this is the T w wall temperature. Okay. And if I say that if I take a small section of this kind, where A dash is the area section, and this is 1 and this is 2. So, in this block of fluid where boundary layer exists, hydrodynamic boundary layer exists, thermal boundary layer exists, in that situations, let us see what is happening and how to go for finding out that integral equations. So, first what we say that say input through plane 1. So, whatever all our analysis would be steady state analysis. So, input through plane 1, that means from this left face, if we see input through plane 1, now mass, how much mass is entering? It will be 0 to h rho V x into dy, correct, and rho into V x is the into dy into 1, already we have discussed in the last lecture. This is the area, rho V x into dy into 1. V x is the velocity in this direction, this is, so you would say x direction, and this is say y direction. So, V x is the velocity in this direction, and in this point it will be V infinity, here t will be t infinity, in this point also t will be t infinity, but V will be V x, okay, because it is the hydrodynamic boundary layer, but here t will be t, t is a variable quantity. So, what we say that V x into dy into 1 is the volumetric flow rate, into rho is the mass flow rate that is entering into, and 0 to h we are considering up till the height, certain height which is above the boundary layer. Okay, h is above the boundary layer. That is what we have discussed. This h is greater than delta t. Now, mass is this, the momentum input, how much? It will be 0 to h mass into again the velocity. So, rho V x square into dy, no problem on that. Then, and energy input, there will be some energy also coming in with this, and that is the mCp delta t, that we know, and reference temperature will be taken as 0. So, what we will write is 0 to h rho into Cp into Vx into t into dy. So, this is becoming the inputs through plane 1. Okay. Now, similarly, if we see output through plane 2, one is input through plane 1, output through plane 2. So, output through plane 2. So, then mass output will be is just same thing at point x plus dx. So, we will get we will write that this is 0 to h rho V x dy at point x plus dx, and this we will write as 0 to h, as we know Taylor's is expansion, dy plus ddx of it is x and dx, x plus dx. Okay. So, this part is dx, correct. And so, d dx of 0 to h whole term rho v x dy into dx. So, that is the output mass. Similarly, we can have momentum out, that would be 0 to h rho v x square dy plus d dx of 0 to h rho v x square dy and whole into dx, that is the momentum out. And then energy, exactly in the similar way, energy would be 0 to h rho C p v x into t into dy plus d dx of then 0 to h rho C p into v into t x, t into this thing whole thing rho C p v x t, okay, into dy whole into dx. That is the energy out through phase 2. Now, in addition to this, there are certain, if we consider, so what is happening, as we have discussed previously, that the momentum is transported from upper direction to the lower direction, and heat is transported in case of heating from the lower to higher direction, because momentum higher fluid above the boundary layer, they have got much higher momentum, because they are moving with a velocity v infinity. Even fluid, any fluid layer above the so as we go ahead, the higher layer fluid will have higher momentum than the layer below to this. Okay. So, the momentum has to be transported from upper layer to the lower layer, and how that gets transported. So, fluid material with this velocity will if it enters, as you can understand that, and when the fluid is moving like this, a fluid element with a velocity v infinity enters into this region, and then it is getting converted, its momentum, its velocity is getting reduced. So, its momentum is taken away by the other fluids in this particular region. So, this is what is going to happen, and that is why the momentum transport takes place. Now, then what we will write is that, so addition of mass. So, because of that, so there will be an addition of mass. So, we will write the through plane AA. If I see that this AA dashed, okay. Now, addition of mass, that will be equal to change of mass is nothing but d dx of 0 to h rho v x dy. This is the change of mass with dx as we move forward. So, into dx. How this mass is coming in the boundary layer? It is coming from the other sides. So, d dx into this is the change of mass. So, into dx is the total mass that is entered extra additional. Okay. And this mass, when it is coming with a momentum. So, associated momentum that is equal to, so they are coming, as I told you, with a momentum of v infinity. So, v infinity into d dx of mass into v infinity, that is all. So, 0 to h rho v x dy into dx, and then it is coming with not only energy, it is momentum, it is also coming with an associated energy. So, associated energy is so we have associated energy is so mCp_T. So, we know that this is mass, and it is entering with a free stream temperature. Naturally, we have discussed, like as it is entering with a free stream velocity, it is also coming with a free stream temperature. So, we should say that Cp into T infinity into the mass d dx of 0 to h rho, I will write again, so I will write Cp T infinity d dx of 0 to h rho v x into dy into dx. So, now we got all the expressions through this, and then other than that there is an energy input from the wall heat is input from the wall. So, that is equal to say dqw, and that will be equal to minus k dx into del t by del y at y is equal to 0. What else is happening in this? There are some forces that is being acting on it. So, what are the forces? We can say that net P. So, forces are pressure force and the viscous force. Already we have discussed this part in different way. Now, for pressure force, so pressure force for plane 1, it is P into say H into 1 is the area. So, P into H is the pressure force, and for plane 2 this is equal to minus of, or it is acting in the opposite direction. So, there will be P plus dP by dx into dx and whole thing into H. So, this is the change in pressure and this H. So, this is acting in this direction and this is acting in this direction, okay, in opposite to each other. So, and there is another part, that is the shear force. So, I will write this as like this way. So, pressure force is P H, and I will write pressure force for plane 1 is equal to minus of that. Okay. We will write like this, at plane 2 is equal to minus of this, and shear force is at the wall minus tau w into dx into 1 is the area, and at the face A dashed, what will be the shear force? 0. The reason is at A dashed, that is shear force means tau is equal to mu into dV by dy. There is no velocity variation, because no velocity variation. So, it is beyond the boundary layer. Okay. Therefore, so then what is happening then, if we apply for momentum integral equation, okay, if we apply Newton's second law, again what it says, that applied forces is giving you the rate of change of momentum in the control volume, and the control volume is that what we have discussed. So, applied forces are minus tau w minus dP by dx into H. If you take up all the this pressure and the other pressure, counter pressure at point 1 and 2, and that would be equal to that net momentum flow out of the control volume. Now, what is this net momentum flow out of the control volume? This is nothing but, if you see, if we just add on all the other things, we will find it. So, it is d dx of 0 to h rho v x square dy into dx minus v infinity d dx of 0 to h rho v x dy into dx. Now, what would this v infinity into d dx of 0 to h rho V x dy, this can be written into dx, also can be written as d dx of V infinity so if I take the differential in, so d is V infinity into 0 to h rho V x dy into dx minus d V infinity by dx into 0 to h rho V x dy dx. So, basically if we do the differentiation of this part, I will get this and this. Okay. So, now substituting this into this, after substitution, what we got is that minus tau w minus dp by dx into h, okay, is equal to minus rho into d dx of 0 to h V infinity minus V x into dy plus d V infinity by dx into 0 to h rho V x dy. Okay, this part. Now, we can say that from in the next if dp by dx is equal to 0 for constant pressure condition, then we know that dp by dx is equal to minus V infinity into d V infinity by dx, that we can find out this from Bernoulli's equation. What is that? And that is equal to 0. What is that? We know that Bernoulli's equation says that P by rho plus V square by 2 is plus Z z is equal to constant, and no elevation, this part is 0 because of no elevation. Okay. Then what we get, dP by dx is equal to minus of rho into V say with respect to infinity velocity at the in the free stream conditions, if we see. So, V infinity d V infinity by dx. Now, if this is equal to 0, so this V infinity by dx is equal to 0, that is then our equation becomes, the previous equation become like this, rho into d dx of 0 to h V infinity minus V x into dy is equal to tau w, and that is equal to mu into del V x by del y at y is equal to 0. So, this is what is called the also what we can write is, this also can be written as rho into d dx of 0 to delta. Now, I will write V infinity minus V x into V x dy is equal to tau w is equal to mu into del V x by del y at y is equal to 0. Now, this equation is called momentum integral equation. And we can see that we have now shifted change the integral limit from 0 to h to 0 to delta, because we know that as and when h is greater than delta, then what happens is v infinity and v x are same. So, this integrand will become 0. So, it will be useless, there is no point. So, it is better to write 0 to delta. Okay. Then, in the similar way, if we see for the energy equation, from energy balance, at steady state, okay, we can write that what is that basic equation is like this: energy convected in plus viscous work with element within element, the element of control volume is equal to heat transfer at the wall plus, or rather if I say that this is also input. So, plus heat input, heat transfer in at the wall, and that is equal to at steady state energy convected out. So, what does it say? It then we can say, putting all the expressions 0 to h rho C p V x t d y plus C p t infinity d d x of integral 0 to h rho V x d y, okay, into d x minus k into d x into del t by del y at y equals to 0, and this is becoming 0 to h rho C p V x t d y plus d d x of 0 to h rho C p V x t d y into d x, provided one thing that viscous work is neglected, already we have discussed. Okay. And then simplification of this gives d dx of 0 to h t infinity minus t into V x into d y is equal to alpha into del t by del y at y is equal to 0. Now, here whether should I put delta or delta t? I should put delta t, because h would be replaced by delta t. That means, or d dx of 0 to delta t, t infinity minus t into V x d y, okay, and that is equal to alpha into del t by del y at y is equal to 0. We have replaced that upper boundary h by delta t, because after delta t, as we have taken the delta t is lower than delta. Okay. So, after delta t, t infinity minus t term vanishes. So, there is no use of that particular equation. Therefore, we will write that as 0 to delta t this. So, this equation is called energy integral equation. So, what we will be doing is, we will be assuming some standard temperature profile, we will be assuming some standard velocity profile for the boundary layers, and then we will be applying putting those profiles into the governing equations. That is what we have developed in the integral equations, and then we will try to find out what happens to the heat transfer rate or heat transfer coefficient, what happens to the friction factor, all these things we can find out. Therefore, this method is called approximate method of analysis, because here what is being done is that we will be assuming the velocity profile, we will be assuming the temperature profile, we will be putting suitable boundary conditions for these particular cases. Now, this equation whatever I have derived now, this equation also can be derived from the basic energy equations and the continuity equations and the momentum equations. So, what we had actually, that if you see that we had the continuity equation is del V x by del x plus del V y by del y is equal to 0. We had V x del V x by del x plus V y del V x by del y is equal to nu into del square V x by del y square. That is the momentum equation. And also we had V x into del t by del x plus V y into del t by del y. Okay. This is equal to alpha into del square t by del y square. So, these are the three equations we had. What we could do is, in case of when we try to find the in the integral mode, that means, if we do the integration of these equations and suitably arrange, we also can come up to the momentum integral equations and energy integral equations. That means, what we can do is these equations can be converted to of this form, like integral 0 to delta del V x by del x plus integral 0 to delta delta is the momentum thickness into del V y by del y is equal to 0. Similarly, integral 0 to delta V x del V x by del t del x plus 0 to delta V y del V x by del y is equal to nu or 0 to delta nu into del square V x by del y square. That means, we are integrating. So, because this is in the boundary layer, if I consider that it is the boundary layer, it is for these equations are applicable for this much. Now, if I integrate, that means it is applicable for the whole section. That is what is being of consideration. So, if you do that, then also we can find out similar kind of results. After that, we have to do some kind of adjustments that we have to do. Similarly, for temperature case, what we have to do is, we have already shown that here the limit should be 0 to delta t V x, because our assumption again, the thermal boundary is below the hydrodynamic boundary layer, V x into what is there del t by del x plus integral 0 to delta t V y del t by del y is equal to 0 to delta t into alpha del square t by del y square. So, this is the integral form of the equations of the continuity, momentum and energy equations. This form of the equations can be, after suitable rearrangements, converted into whatever I have discussed with the help of the cell balance approach. Okay. Now, what we have to do is, as I told, that our analysis, next part of the analysis in the boundary layer is to find out a velocity profile, to find out a suitable temperature profile, and to get put these velocity and temperature profiles into the basic governing equations, and then try to come up with a solution which is a approximate solution for heat transfer coefficient or for friction factor. So, in our case, most important thing is the heat transfer coefficient, and what I will discuss at present is, I will give a simple question. That the question says that if I say how is the velocity we have seen, it's a kind of nonlinear velocity profile. So, if I say in a boundary layer, say V x is equal to a 1 plus b 1 y plus c 1 y square plus d 1 y cube, how to get the velocity profile? So, we can understand this is a third order polynomial with 4 constants, unknowns. These unknowns are A1, B1, C1 and D1. So, to get these 4 unknowns, what we have to do? What are the boundary conditions that we have to put? So, we have to put several boundary conditions, or rather 4 boundary conditions are needed. Okay. What are these boundary conditions and what is the velocity profile? So, we can say, if we can say that as this is the boundary layer, hydrodynamic boundary layer HBL. Now, this is the wall, flat plate, and flow is in this direction. This is V infinity. So, it is understandable. So, this is V x. So, what will be the boundary conditions? And we see the first one at y. So, this is y and this is x. So, at y equals to 0, because we have to find out with respect to y, not with respect to x, but to find out with respect to y, because v is a function of y. V is moving. V is not function of x, that we are not considering. We are considering v is function of y. So, what is happening is at y equal to 0, what is happening? V x will be equal to 0. That is the no slip condition. Then at y is equal to delta, okay, this is when it is reaching to the boundary layer, so it is delta. At y is equal to delta, V x is equal to V infinity, that is the free stream velocity. Then that is happening for any value of x, it is happening for any value of x. Okay. And then at y is equal to delta, again we can write, already we have seen that shear stress at this point we are assuming to be 0. The reason is there is no velocity gradient. So, V x is equal to V infinity. So, therefore, we will write that del V x by del y will be equal to 0. Okay. And then what more? Another boundary conditions. What is that? So, that is at y is equal to 0 again, we will write del square V x by del y square equals to 0. How? We know that if we write the integral momentum equation, that V x del V x by del x, V y del V x by del y is equal to nu into del square V x by del y square. And what we know that when y equal to 0, this is equal to 0 and this is equal to 0, both will follow the no slip condition on the plate wall, x direction or y direction, both the velocity should be 0 at y equal to 0. That means, so del square V x by del y square will be 0. So, this is the another condition that we could generate from the continuity equation. So, when we have an expression of this kind, we can find out the boundary conditions, and once the boundary conditions are known, what we have to do? We have to find out. So, V x is equal to a 1 plus b 1 y plus c 1 y square plus d 1 y cube. So, we will find out del V x by del y is equal to a 1 plus b 1, sorry, a 1 gone. So, as because it is, if we say the V x is only function of x, so what we will write now? We will write it in the perfect differential form. So, we will write d V x by d y is equal to b 1 plus c 2 c 1 y plus 3 d 1 y square. Similarly, d 2 V x by d y square we will write as 2 c 1 plus 6 d 1 y, like this. And then we will put the conditions, and then what we will get is that y is equal to, or our expressions will be that V x by V infinity is equal to 3 by 2 y by delta whole to the minus half y by delta whole cube, and this is equal to 3 by 2 eta minus half eta cube, where eta is equal to y by delta, dimensionless distance along y direction. Okay. And this is a very famous velocity profile, which is nonlinear velocity profile. Similarly, for temperature, exactly the similar thing you can do. So, what you can do is that, so we will assume that t is equal to a 2 plus b 2 y plus c 2 y square plus d 2 y cube. And then what will be the conditions? That at y is equal to 0, we have t is equal to t wall, that is 1, and also we have del 2 t by del y square equal to 0. That is what we have seen, and at y is equal to delta, we have t is equal to t infinity, and we have del t by del y is equal to 0. Now, if we assume t is only function of y, we can write it to be as d 2 t by d y square equal to 0, and we can write as d t by d y equal to 0, when t is function of y only. Okay. Then exactly putting the same way, we can get the t minus t w by t infinity minus t w, which is the velocity temperature profile, and that should be 3 by 2 y by delta t. Here it should be delta t, the thermal boundary layer thickness, into say minus half y by delta t whole cube. Okay. So, if I say that this is equal to say 3 by 2 eta 1 minus half eta 1 whole cube. So, eta 1 is equal to y by delta t. So, it is again a dimension. So, we can understand one thing, that there are a lot of similarities between the heat and momentum transport, and from there we will see in the next lecture, we will try to find out, after putting such kind of velocity profile or temperature profile, how to find out the expression or value of heat transfer coefficient. Okay. Thank you very much.